In this video, we are going to take a look at second law of thermodynamics. And one point that the second law makes is that efficiency is never 100%. So let's look at a couple formulas we can use to compute efficiency. E equals 1 minus the final temperature of the system over the initial temperature of the system. And the other way we can compute efficiency is the work out over the work in. Now these two expressions don't compute the same thing. And the difference is we can use, we'll call this efficiency 2, efficiency 1. Efficiency 2 is a working definition that we can use to compute the efficiency of a very real-world system that is actively doing work. Whereas we can use the first efficiency expression to compute the maximum or the limit of how efficient that system can be. And so just so we have some variables here, T equals temperature, work out, work in, we will compute using joules, so energy. And so we can look at an example. Let's say we have a system we want to compute the limit of efficiency of an engine, and we know the measurements or the data points we have are the initial and final temperature. Simple enough. So let's say the final temperature is 300 Kelvin and the initial temperature is 500 Kelvin. We could plug this into the expression 1 minus 3 over 5 equals 2/5 or 40% efficient. So we could say that this system has a 40% efficiency, and that's the maximum it can have. Now, alternatively, we could see how much efficient an experimental engine is. So let's say we just grabbed an actual engine. Before, we didn't have an actual engine. We just knew two data points, and that was the temperature. But now we have heat entering the system. In fact, we actually need another formula here. And this is really the first law of thermodynamics, which is enthalpy, or the heat of a system, is equal to the work it does on the external environment plus the change in its internal energy. And let's say we know how much heat we added, which is 16,744 joules, and the work it did, which equals 5,000 joules. And so we can find that the heat available to do work is going to be equal to the difference of these two guys. So basically we're just subtracting the W over. So 16,747 minus 5,000, which equals 11,744. And this is expressed in joules. We can also express this in kilocalories. We do 11,744 divided by 4,180. That's how many joules are in 1 kilocalorie. And we get 2.8 kilocalories. If you think about this on much smaller scales, we can talk about calories, so food we consume, the energy involved in the chemical processes and biochemical processes. So now we have to use our working definition, which is work out over work in. What is our work out? Work out is our 5,000 joules, as we've already stated, so that was a given. So we have 5,000. And then what's our total work in the system? Well, that was also given, actually. And that was 16,744. And so the computed efficiency of this specific engine that we looked at, or experimentalists look at, is roughly 2.9, or 29%. And this is the first law of thermodynamics. Efficiency is never 100%.